Hello everyone, good evening. Good evening, Saimi. Who all are there? All of you, please type in your name. Hello, Ritvik, Sanjana, Vaishnavi. Okay, so today we are going to solve questions of thermodynamics. Okay, thermodynamics questions we are going to see. On the screen, you can see that I have given you the first question. You can start solving this. Hello, Lalita, Shreyash, Sundar. Please solve this question, the first one. Tell me the answer, first question. Okay, so most of you are saying D, Saimir is saying C, Vaishnavi is saying C. Okay, tell me first of all, the first option, option A, what kind of system it is? The presence of reacting species in a covered beaker is an example of open system. What kind of system is it? First, option A. Option A is a closed system, right? Option A is a closed system. Option B, you see, there is an example of energy as well as matter between the system and surroundings in a closed system. It's not possible, right? Second option is nothing but an open system, right? First one is closed. Option B is an open system. The presence of reactants in a closed vessel made up of copper is an example of closed systems. C option is correct because copper vessel is what? Is not an insulator, right? Closed system are those systems in which the exchange of energy takes place but matter cannot be exchanged, right? So in the option C, since it is a copper vessel, so exchange of heat possible, exchange of energy possible, but since it is closed, so Matter exchange is not possible in this. Okay, so C option is correct, first of all. D option, you see the presence of reactants in a thermoflask or any other closed insulated vessel is an example of closed system. No. Option D is what? What kind of system? Option D is what kind of system? Option D is. Tell me. What all different types of system we have? First of all, you see, we have open system, then we have closed system, and what is the third type? Third type is insulated system, right? Insulated system. So in all these three type, you see, in open system, exchange of matter and energy both possible. Matter and energy. Closed system, only energy transfers, right? Insulated, no matter, no energy. There's no transfer of matter or energy into insulated system, right? So the option D, you see the presence of reactant thermoflask. Thermoflask is what? Thermoflask is a insulated system. We consider thermoflask as an insulated system, right? Or any other closed insulated vessel, right? Closed insulated vessel it is. Since it is closed, so obviously matter cannot transfer, right? Now it is insulated also, so energy also cannot be transferred, right? So this is not an example of closed system, but this one is for insulated system, right? This is insulated, this is closed, and this one is open. So option D is correct here. Clear? Next question, you see. Solve this one. Lolita is getting C, Saimir is getting B. Tell me others. Try to recall the concept of reversible and irreversible process. And what are the major points we have over there in both the processes? B. Why it is B? Saimir and Lolita, tell me. Okay, so most of you are getting C. Simon and Lorita is saying B. Why it is C, Vaishnavi, Sanjana, Amog, Shreyas? Why it is C? Compressed to high pressure, so I thought reverse would happen. Okay. Okay, you remember this. Okay, now you see the pressure volume work for an ideal gas can be calculated by using the expression, and this is given P external into dV. You see here they are talking about only magnitude. Okay, work done is what? Work done is equals to minus of P external into dV. This is work done, VI to VF, right? But here they have taken only integral of this. Okay, there is no negative sign. It means they are talking about the magnitude of this work done, right? Right. So work can be calculated from this P plot by using the area under the curve within the specified limits when an ideal gas is compressed reversibly and irreversibly. From Vi to Vt, choose the correct option. Okay. So you see, first of all, they're talking about magnitude here, not the work done. Right. Work done is minus P external into dV, but they're talking about magnitude here. Right. So we know what work done in an reversible process is always more than irreversible. Just a second. Hello, Gaurav, it is. Yeah. No, no, I'm a bit busy now. Can you call me tomorrow morning around 11? Yeah, yeah, yeah. Correct. Sure, sure. Okay. Thank you. Bye. Okay, so here work done in reversible process is always more than the work done in irreversible process, right? So it means what? The magnitude, since we are talking about magnitude here, so since work done, small, mistake you have made here, work done in reversible process is more than the work done in irreversible process. Irreversible process. But this work done actually includes the negative sign also, right? So it means what? If you talk about the magnitude of work done, then the magnitude of work done in reversible process should be less than the magnitude of work done in irreversible process. Understood? So here in this case, the answer will be option B. Correct. The only thing is that talking about the magnitude, not the work done, because expression they have given. They can give you simply work done also, but they have given the expression here. This is not work done. Work done in negative of this, right? So if work done in irreversible process is more, it means its magnitude is less since negative sign is there. Is it clear? Tell me any doubt. So all of you know already this fact. Okay, but the only thing that you missed over here, they have given the expression. This expression without negative sign is not work done, right? So we have to talk about this expression. It means we are talking about the magnitude of work done. So W is nothing but here it is the magnitude of work done, right? That's why option B is correct. Third one. So direct formula, tell me. Amok is getting D. Sanjana is getting D. Vaishnavi D. Amok B. Oh, Amok is getting D. Saimir is getting B. Check your calculation. I think option D is correct. Minus P delta V you have to use because constant pressure is given. When constant pressure is there, then what kind of process is this? Can you tell me? When it is a constant process, pressure, then what kind of process is this? Isobaric. If I ask you reversible or irreversible, then if I ask you reversible or irreversible, then reversible. Is it reversible? Tell me others. It is irreversible process. Yes, Amog, when constant pressure is there, sorry, there, then the process must be irreversible. It cannot be reversible process. Reversible process, the external pressure is not constant. You keep on decreasing pressure by some value. Okay, small amount, and then the process takes place. That is reversible. Okay, so two things we have discussed. So the formula we'll use here is what? Work done is equals to P delta V. Okay, that will be external dV minus P is nothing but 10 to the power 5, and the volume change is what? 10 to the power minus 2. Vf is 10 to the power minus 2 minus 10 to the power minus 3. This is what you need to solve. Okay, so I think 10 to the power minus 3, you get 900. Option D is correct. Okay, next question you see. This one, question number 4. Question number 4. Okay, some of you are getting A, D, Amog is getting C. I think option B you can eliminate easily, right? Because Q does not equal to 0. See here, the process is adiabatic. So for adiabatic process, we can easily write Q is equals to 0. This is for sure we have. Hence, option B is not correct, right? Now, no transfer of heat takes place between system and surroundings, right? Choose the correct option for free expansion. Okay. So work done also we have to find out whether it is 0 or non-zero. and work done takes place. Work done will be there because of the process. Okay, and what process is there? The process is expansion. Okay, and what kind of expansion? Free expansion. See, expansion, we have two types of expansion. You must have studied this. Suppose you have a piston cylinder system, right? Two system we are taking. Okay. Now suppose here the external pressure P external, we have something, right? And once you decrease the external pressure, the expansion takes place, right? So when the P external decreases by some value, this value can be anything, right? Then what happens? Expansion takes place. So there are two possibilities. Either we can decrease this external pressure by some value, or what we can do here P external, we can all of a sudden reduce this pressure, the external pressure, to zero. So in this, another process is what? If the P external, all of a sudden we make it to zero, then also expansion takes place, right? Expansion takes place. So these are the two different types of expansion we have. One is what? When external pressure is reduces by some value, and another one is when external pressure you becomes all of a sudden it is zero, right? So this kind of expansion, when external pressure you are decreasing by some value, we call it as intermediate expansion. Intermediate expansion. And this kind of expansion, when external pressure is zero, we call it as free expansion. So here in this question, we are talking about free expansion. So what we can say, in free expansion, the external pressure is what? The external pressure is zero. And since when external pressure is zero, work done will be equals to zero. Right. So when work done is zero, so you can easily eliminate again option D. Correct. Now we can use the first law of thermodynamics, that is the change in internal energy is equals to Q plus W, and both is zero, so del U is equals to zero. So change in internal energy is equals to zero. It means we have constant temperature, because internal energy is a function of temperature only, right? When constant temperature is there, then what we can write, delta T is equals to zero, right? So this is what option C is, right? Clear? Next question. Yes, Del E or del U, both are same thing, change in internal energy. Okay, why it is B? Yeah, correct. Option B is right. See, this is the key point you have. Must you keep this in mind? Whenever you have question of internal energy, you must remember this, that internal energy, which can be represented by capital E or capital U, both are, this internal energy are the function of temperature. So when temperature is constant, then the change in internal energy del E or del U is equals to 0. So in isothermal process, right, or cyclic process, so what we can say, in isothermal process or cyclic process, in cyclic process what happens, the both initial and final state are same, right? And temperature is what, temperature is a state property. When you are at this point, the temperature will be same, right? And if you come to this point again by any, by followed by any other path like this, if you are here only, which makes a cyclic process it is, since initial final position is this, so initial and final temperature is also same, and that's why the change in internal energy will be 0 in this case. So whenever we have isothermal or cyclic process, the change in internal energy is 0, right? You see in this case, isothermally it is given clearly, del E is change in internal energy, so it will be 0. Okay. Okay, Amog is getting C. I'm waiting for others to respond. Simon is also getting C. Okay, tell me guys, two more response, then I'll solve it. What happened, guys? Should I solve it or you are still trying? Okay, I'll do this. See, okay. So 1 mole of CO2 gas at 300 Kelvin expanded under adiabatic condition such that the volume becomes this times what is the work done. Okay. So from first law of thermodynamics, what we can write, we have to find out work done. Okay. So change in internal energy delta E is equals to Q plus W. This W is the work done by the system, right? Because it is expansion. Okay. Now, since the process is adiabatic, so Q is equals to what? 0. Q is equals to 0, right? And hence del E is equals to W, where this W is actually work done on the system. Sorry, it is work done on the system, right? Now, the second thing is what? This is the mathematical thing we are getting. Okay. Now you see adiabatic conditions such that the volume is increasing, right? And since it is an adiabatic process, so there is no exchange of energy between system and surroundings. So whatever expansion takes place, that will be there at the cost of the internal energy of the system, right? In adiabatic process, whenever expansion takes place, so expansion takes place at the cost of its own internal energy. Internal energy. So it means what? that internal energy of the system is decreasing, right? And hence we can say that delta E is negative. Change in internal energy is negative. So the work done of the system will be what? If I include the sign convention here, work done will be change in delta E, right? And this delta E we can write CV delta T, T2 minus T1. Okay, CV value is given 6 calorie per mole, right? And T1 is also given 300 Kelvin. Okay, we have to find out what T2 and then we can find out work done. Okay, so now to find out this T1, we have the relation of volume. Suppose if I write down the relation for temperature and volume, because volume thing is given, right? So suppose if V1 is V, so V2 will be 27 V, right? T1 is 300 and this T2 we do not know. So we have to find out the T2 and then we can substitute here, we'll get the answer. So what formula we can use? The relation of temperature and volume in adiabatic process. T2 by T1 is equals to V1 by V2 to the power gamma minus 1. Right? V1 by V2 is nothing but 1 by 27. Right? So we can use T2 by T1 is equals to gamma is 6, 6 minus 1 is 5. So 1 by 27, 1 by 27 to the power, I think some mistake I have made. 1 by gamma minus 1. Oh, gamma is not 5. No, gamma is 1 point. Oh, correct, correct. This to the power 0.33. Okay. Now you can solve this and you'll get T2 from this. How can we solve this? 1 by 27 can, to the power of this, can 1 by 0.33 we can write 1 by 3 into T1 is 300 Kelvin. So when you solve this, T2 is equals to 100 Kelvin you will get. Okay, so this value will substitute here and work done is equals to minus 6, T2 is 100 and T1 is 300. So you'll get 1200 calorie. Answer is option C. Understood? So what we can, what one point what we can keep in mind, which may they ask in theoretical question, whenever you have adiabatic process, right? An expansion. See, actually, one thing you can observe from this question, okay, and this kind of observation is actually required, and that is what we talk always these things. You see, what you can observe from here, that expansion in adiabatic process, T1 is 300 and T2 we are getting is 100 Kelvin. So what happens here, whenever you have expansion in adiabatic process, the temperature decreases. T2 is less than T1. And when the temperature decreases, then cooling takes place. Clear? So this is what you can keep in mind, that whenever you have adiabatic process and expansion takes place, then final temperature will decrease and cooling takes place. Right? Remember this point. Next question. Okay, do this one. Amog is getting D. How it is D, Amog? Change in internal energy. Amog, read the question carefully. Is it a cyclic system? Don't get confused with the graph. Read the question carefully. Correct, Sanjana. Yes, that is what you have to keep in mind. Internal energy is a state function. Correct. Yeah, right, Sanjana. Okay, see, a system is taken from state A to B. Correct. So this is A to B. There are two paths. One is ACB and other one is ADB. So it is not, since we are talking about these two paths, ACB and ADB, right? So this graph is a cyclic graph, but the question does not is not about the cyclic process. Correct. First thing is that it would be a cyclic process according to the question when we talk about ADBA or ACBA. Then it will be a cyclic process. What happens here? The initial state is at A and final state is at B. Here also initial is at A and final is at B. So initial and final position for these two processes are not same. So this is not the cyclic process we have. However, the graph is cyclic, right? So now you see here, first of all, when a system is taken from state A to B along path ACB as shown in figure, 80 joule of heat flows, right? So Q is equals to plus 80 and W is equals to minus 30. right? So we can find out delta E over here. That is Q minus W, which is nothing but 80 minus 30. Minus means plus will take, if you take convention here, then it becomes minus. And that will be 50 joule of internal energy. Now the point here it is what? Since internal energy is a state function, okay? So when you go from A to B, from this path ACB, internal energy is 50. So when you go from A to B from this path ADB, then also the change in internal energy will be 50 only, because the initial and final state are same. No matter what path you follow, the change in internal energy will always be 5050, right? So delta E we have, right? Work done is also given, that is minus 10. So we can find out Q, that will be equals to delta G, or sorry, delta E plus W, and that will be 50 minus 10 is equals to 40 joule. Correct. Okay, so you are getting Q is equals to E minus W. Okay. Okay, just a second. So H C to B delta E is equals to Q plus W. That is 50. So when you talk about E, Q is equals to E minus W, right? Just a second. It's correct only, no? You see, first of all, what happens? Delta E is equals to Q plus W. Okay. So the first state that you have from A to B from C via C, when the system is taken from A to state B along the path ACB as shown, 80 joule of heat flows into the system. So this heat is flowing into the system. So Q is positive over here, right? And system does 30 joule of work. So obviously you are giving 80, you have a system here, you give 80 joule of heat, and out of that 30 joule is going into work. So what is left? We are left with 50 joule. So this is will be into the system. It will be stored into the system. So internal energy will be 50 joule, right? Which is here also. Now the system has 50 joule of energy from here to here if you go, right? And in this process, if you follow this path ADB, 10 joule of work is done, right? So here you see what happens. You see actually when you compare from this to this, no, you'll get confused. Okay, don't think like that. Here you simply think that system is going from A to B. The change in internal energy is 50, right? But in this case, what happens? We are not putting into any heat into it. Like here you see 80 joule of heat flows into it. But in the second case, there is no heat flow. What happens? How much heat flows into the system? We have to find out this. Okay, how much heat flows into the system along the path if work done is 10 joule, right? So what should be the value of heat should be flown into the system so that the work done is 40, right? So work done is 10. So what happens? We have 50 joule of internal energy from here to here, right? And 10 joule of work done is there, right? And this work done is what? Right, this work done is on the system, right? So that's why it is negative. So 50 internal energy you have already, right? And 10 is the work done by the system on the system, right? So if it is 40 only, then 40 plus 10 becomes 50. Correct, you can think in the other way also. See, actually what happens here, first of all, you do not compare these two formula here. This is, I know this is a bit confusing, right? We get 50 joule of internal energy, fine. Now we'll come back to the second part of it, right? What happens? How much heat flows into the system so that the work done is 10, right? So change in internal energy is 50 only, right? Change in internal energy is 50 only. So what happens if, see, work done is negative here, right? 10 joule is negative. So 50 you have already into the system, right? And the negative work done is 10, right? So what should we provide over here? Q value. That will be 50 minus 10, 40. That is what we are getting here. Okay, so what we are doing work on the system. So you are giving heat to the system, right? So system is not losing heat. So won't heat increase? 50 joule of heat is there and 10 joule work, right? See, you can think like this also. When any system, when you provide heat into it, suppose 100 joule of heat if you provide, right? So out of 100 joule, right? If suppose 50 joule of work is there, then internal energy will be 50. 100 minus 50 will be 50, right? So internal energy is positive, correct? Internal energy is positive. Now you see, if this work done is negative, if this work done is negative, then it means what? We are doing work on the system, right? So internal energy will be what? 100 plus 100 minus of 50, that will be 150. Like this here, if you see 30, 10 joule of work is there, and this work is 10 joule, which is minus 10. which is minus 10, right? And if this would be x, see, minus 10 is the internal energy, right? It's giving in. So heat that you are giving in is x, so that the internal energy becomes 50. What I said here, 100 minus 50, that will be the internal energy if negative work done is there, and it will be 150, right? So if the negative work done is there, right, so x minus of 10, it should be 50, and that's why x is equals to 40. It's just the convention, you are taking it from the different in a different way. So I'm getting it 40 only. See, negative work done means what? Work is done on the system. Is it clear? Just the example, you try to understand this example. 100 joule of heat you are providing into a system. And if the system does some negative work, 50 joule, so what will be the total energy of the system? 100 minus 50. That will be 150. We are adding these two simply. Similarly, here suppose I am providing x joule of heat into a system, and if it does minus 10 joule of work, so what is the internal energy of the system? X minus 10, and that will be nothing but 50. X equals to 40. Is it clear? One thing you just keep in mind, just one thing. When negative work is there, it means the same amount of energy, by the same amount of energy, the internal energy of the system is increasing. Right? One more thing, like this also you can understand. I can explain you like this also. Say one thing like you understand like this. You have a system, right? And in this system, if you provide 50 joule of heat and system is not doing any work, what is the internal energy of the system? Tell me. When no work is there, what is the internal energy of the system? It will be 50 joule. When no work is there. Correct? Now, what happens? You are providing 50 joule of heat into it, and system starts working, right? And suppose if it does 10 joule of work, so how the from where this 10 joule of where this energy is coming? It is coming from the heat that you are providing in. So out of 50 joule, 10 joule of heat is required, or it is utilized in the work done by the system, right? So internal energy of the system will be what? 50 minus 10, that will be 40. Correct? If 20 joule of work done is there, then again the heat that you are providing in, with that only the system is doing work. And if it is 50 joule, then 50 minus, so if it is 20 joule, then 50 minus 20 is equals to 30 only, right? So what happens whenever the positive work done, then the internal energy of the system is what? It is decreasing. It will be less than the energy that you are providing in, because the same energy the system is utilizing in the work. Now, if the work has negative work done, like suppose minus 10 joule you have, it means you are the system, we work done on the system we have over here, right? Means we are doing work on the system, 10 joule of work on the system. You are providing 50 joule of energy into it, right? And 10 joule of work done is there. So accordingly, if you calculate, it will be the answer that we have here. Correct. So it's just the thing, you may get confused with this, since it is del E is equals to Q plus W. So Q is equals to del E minus W. I think you are getting the relation from here. That's why you got confused. But it is all about the convention. the work done by the system or on the system. Accordingly, you have to think. Okay, it's not the formula you can relate directly at the 2 point. Right? Next question you see based on this data only. You see this question. When a system is taking from A to B along the path C, okay, first part is same, the information given is same. The second part is what? When the system is returned from state B to A along the curved path, okay, the curved path that you have, work done on the system is 20, the system absorbs liberated heat into it. Tell me the answer of this one. Here you see work done on the system. So W is equals to what? Minus 20 joule. Del E we have calculated already. That is 50 joule. Okay. What we have to find out, does the system absorb or liberate heat? And if it is, then how much? Okay. So we can use this del E is equals to Q plus W. Right? Del E is 50, Q, W is minus 20. So Q is equals to what? 70 joule. Now, what is the meaning of this 70 joule? Initially, it was 50. Right now, it becomes 70. So obviously, the energy has been absorbed. Right? And the value is in 70. So answer B is correct here. Right? B is correct. Also, all of you have done this. Next question you see. This one. Question number 9. See, I'll give you one hint here. Heat absorbed in the process of dB. Okay. So first of all, you find out what is the change in internal energy when the system goes from D to B. That del E you find out. Okay. We have to find out the heat absorbed. Means Q you have to find out. Del E you can get easily because from A to B you have A to D is given. So you can find out from D to B. So find out the energy involved or the work done from D to B, right? Heat energy, internal energy from D to B, and then use first law of thermodynamics. Molalita, Sanjana, Sam here, all of you are getting D. Okay, D is the right answer. D is correct. You see this, I'll solve this one quickly. Del E from A to B is equals to the change in internal energy from A to D plus change in internal energy from D to B. Okay, since the question is for DB process, so we required this only. Change in internal energy from D to B. And which is nothing, it is 50. It is 40. So change in internal energy from D to B will be 10. It is 10 joule of heat. Now in this, if you apply first law of thermodynamics, so that will be equals to Q from D to B plus work done from D to B. Now you see work done in this process, since D to B process is what? Constant volume. D to B is constant volume. So work done is equals to 0. So Q is nothing but D to B is nothing but 10. So that is what we have. The heat absorbed is 10 joule. Right? Question number 10. Done? Try to use the fact that work done in reversible process, when the process is adiabatic expansion, it is maximum. Okay.
So work done in reversible adiabatic expansion is maximum. Use that process. Why it is A, Lalita? Okay, see, we know this fact that work done in reversible adiabatic expansion is maximum. Maximum means in comparison to irreversible, reversible we have more value. Okay. So when it is maximum, it means the system will use more, the energy of the system will be more utilized in case of reversible process, right? And hence the temperature will be less. So option A is correct. Just a second. Hello. Hello. Yeah. Yeah. Hello. Tell me. Right. Delivered. आ जाओ. हाँ सेंट जॉन से आओगे ना तो आपको वो दिखेगा. एक सेकंड रुको. Just a second, I'm coming back. हाँ जिस सेंट जॉन से वेब से आओगे ना सो आप स्ट्रेट आना आपको दिखेगा वो आईसीआईसीआई बैंक और आई पार्टी को दिखेगा. ठीक है. आपको आई लेफ्ट साइड में आईसीआईसीआई बैंक दिखेगा. ठीक है. और आपको आगे जाके यू टर्न लेके आना है. मतलब आप आईसीआईसीआई बैंक दिखेगा आपको. आप उसके ऑपोजिट साइड देखोगे ना. ऑपोजिट साइड मतलब इधर की तरफ राइट साइड देखोगे आप तो आपको एक स्कूल दिखेगा गवर्नमेंट स्कूल. उसके बगल से एक गली. हाँ उसके बस जस्ट बगल से गली आ रही होगी अंदर. ठीक है. फर्स्ट में स्कूल के जस्ट बाहर. मतलब आप जैसे आईसीआईसीआई बैंक के ऑपोजिट देखोगे आपको दिखेगा स्कूल. हाँ स्कूल के बाद आप लेफ्ट हैंड है ना सीधे आओगे आपको आपको एक्सिस बैंक एटीएम दिखेगा. ठीक है. एक्सिस बैंक एटीएम से आप लेफ्ट ले लेना. क्रॉस में डेड एंड है ना वहीं पे खड़ा. ठीक ठीक. Yeah, okay. Sorry. So the thing is, work done in reversible adiabatic expansion is maximum. That you know already. Okay. Now, when more work done is there, it means what? The more energy of the system has been utilized, right? More energy of the system is utilized. It means the heat content is less over there, and hence the temperature will be less, right? So what we can say, the final temperature in case of reversible process is lesser than that of irreversible process, and hence option A is correct. Okay. If you have two systems, like you see, if you try to understand like this, two system you have, one is going under reversible change and other one is going under irreversible change. So since the work done is maximum than this, it means the energy of this system has been utilized more and hence its heat content will be less. Content is less, and we can say the final temperature is also lesser than the other case.
No, it's not. That's what I'm explaining, Amog. What is the doubt you have? Tell me. When the work done is more, it means more energy of the system has been utilized, and hence the temperature will be less. System is doing work, right? Yeah, system is doing work, right? When system does more work, it means its energy will be less, right? And hence the temperature is also less. Correct? All of you understood? Tell me. Can we move on? Okay, question number 11. Do this one. Question number 11. What is the answer? This one is easy, right? When constant volume is there, so work done will be 0. And when work done is 0, only third option is correct. You see? Third option is correct. Right? Constant volume, hence work done is 0. That's why C is correct. Question number 12. Question number 12. Tell me. 395 joule approximately. Yeah, you can take that approximation. Option B you are getting, right? Okay, see, option B is correct. B is the right answer. You see, a gas present in a cylinder fitted with a frictionless piston expands against a constant pressure of 1 atmospheric. So, first of all, the information we have is what? We have constant pressure. And when constant pressure is there, it means the process is irreversible. And in irreversible process, the work done is what? Minus P delta V or dV, P external into dV, right? So work done we can find out because it is given pressure is 1 and volume is 6 minus 2, that is equals to 4, right? Minus 4. And the unit of this is what? Liter ATM, right? Which you have to convert in the joule. Liter ATM you have to convert in joule, and that will be 4 into 2 calorie almost if you take 2 divided by 0.0821. This is the work done, okay, in joule approximately. Or this liter ATM you can directly convert into joule. That conversion you have already. The same thing I have done here. Now we can use the first law of thermodynamics because you see the question is what? In doing so, it absorbs 800 joule of heat. So Q is equals to what? The data is given plus 800 joule. The increase in internal energy del E. So del E is equals to what? Q plus W, which is nothing but 800 plus, when you solve this, it will be around minus of 800 into this and 405 joule. So 800 minus 405. So approximately you are getting minus of 395 joule. Hence option B is correct. So from the first data, constant pressure, the process is irreversible, hence work done is P del V. We can find out work done here and then we can use first law of thermodynamics. We'll get the answer. Clear? Understood? Next question you see. Can we move on? Tell me. Question number 13. This one. The figure is not given. Let me just cross check. I'll show you the figure. The diagram is this. We have pressure volume diagram. This one here we have P1, V1 and T1. This one we have P2, V2, T2, P3, V3, T3. This one is adiabatic, and this one is isothermal. Now you tell me this question. This is the graph. Thirteenth, Amog is getting D. Okay, so in the previous question, how 8 by this is 395? You're not getting 395. It's not 8, it's 4, I think. Let me check once. Just a second. Question number 12, right? See, you can use this also, this relation also. 1 liter ATM is equals to 101.33 joule. That also you can use. So if you have 4, so that will be approximately 405. That's what I've taken. It's 405, not 395. Sanjana. Or if you use directly 4 ATM liter is equals to what? 4 into 101.3 joule. And that is approximately 405 I have taken here. Right. Next question. What is the answer in this one? You have to find out incorrect statement. All of you are getting C or D. Okay, chalo, we'll discuss all these options one by one. See, first of all, from this point to this point, the process is what? The process is isothermal. Hence, T1 is equals to T2. So option A is correct. We have to find out incorrect statement. Okay, Sanjana is getting D. So T1 and T3. What is this process? This process is adiabatic. And this is nothing but adiabatic expansion. Adiabatic expansion, right? Volume is increasing. So we know in adiabatic expansion, just now we have discussed one question. In adiabatic expansion, cooling takes place, right? 100 Kelvin and 300 Kelvin, the question was there. Cooling takes place. When cooling takes place, it means the temperature will decrease. So T3 should be less than T1, right? But in the question it is given, option it is given T3 greater than T1. So this is the incorrect statement we have first of all, right? Other option we'll see. Work done in isothermal process is greater than adiabatic. So obviously the work done in isothermal process or the area occupied by the isothermal process here, it is obviously more than the area occupied by the adiabatic process. Hence option C is also correct. Right? Option C is also correct. Change in internal energy. How do we find out this? We know the change in internal energy is equals to NCV delta T, right? So change in internal energy for isothermal process, that will be zero because delta T is zero, isothermal process. And for change in internal energy for adiabatic process, that will be what? NCV. For adiabatic it is T3 minus T1. T3 minus T1. And since it is adiabatic process, expansion takes place. So work done by the system. So internal energy decreases. So del E will be negative. So T3 is less than T1. Right? Oh, this is one thing that we have already done. Delta E is negative. So if you compare these two, this is 0 and this is negative. So delta E in case of isothermal process is more than to that of delta E in case of adiabatic process. So option D is also right. B is the wrong option we have, and that's why the answer is B. I think you forgot this part, right? Yes. You forgot, no, the second option, you forgot this one. Cooling takes place and all. That's why I mentioned that this time. That these are the conclusion we have. Must remember this. These kind of things you should write down the notes so that you will revise this in the last day of the exam. Okay, so that's this kind of key point you should note it down. Next question you see. Question number 14. Got it? Done? Okay, use the relation of enthalpy and internal energy. There is a formula or equation we have for enthalpy and internal energy. Use that. What will be the delta Ng for this question? Okay. What is the question? See, the question is what? That what will be the change in internal energy for 3 moles of liquid? Okay. And since latent heat of vaporization they are talking about, so obviously the question is what liquid is converting into vapor, okay, which is not given, but with latent heat we can say the liquid is converting into vapor, right? So delta Ng is what? It is only for gaseous molecule, right? So you only take the number of moles of vapor. Liquid you don't consider into this. So that will be 3 in this case. Understood? Now you try this. What about others? Did you get the same answer? Option C. Shreyas, you there? Sanjana? Ritvik? Where is Lalita Vaishnavi? Okay. See, use this formula. I'll tell you this. Delta H is equals to delta E plus del Ng RT. That is it. Everything is given. Just you have to find out this del E. That is what the question is. See, delta H will be what? Delta H will be 30 because this is 10 kilocalorie per mole. Shreyash, maybe you have made the mistake over here. It is 10 kilocalorie per mole, but we have 3 moles here. So delta H will be what? It will be 30 kilocalorie for 3 moles. Do it, you'll get the answer quickly. R value you take 1.9 or 2 better you take because it is kilocalorie. Okay, take 2 and then convert into kilocalories. 2 into 10 minus 3. So you'll get C. So del H is 30. Del E you have to find out. Delta Ng is 3. R is 2. Temperature is 500 and 2 will convert into kilocalorie minus 3. Understood? Clear? Next question. $15.
Hello. Hmm. Welcome. Oh, I don't. Here it is. Yeah. Excuse me. थोड़ा noise करो.
Okay, did you get the answer? This question is also same, just you have to use the same formula. Del H minus del E, so you have to find out this value, del Ng RT. This is the answer in this question. Okay, formation of carbon monoxide from its elements. So first of all, we have to find out this del Ng RT. Temperature is given. Only thing is required is what? Delta Ng. Okay, so formation of carbon monoxide. So what should be the relation here? Equation, sorry. Carbon solid, half of O2 gas, and this gives CO gas. So from this equation, you can find out delta Ng, which is nothing but 1 minus 1 by 2. Now you substitute here and you'll get the answer. I think option D is correct here. 15th one, option C is correct. 15th one, option C is correct. Check your calculation. I think D is correct. Answer given C, but I don't think minus sign will be there. It is 1 minus 1 by 2, so it is positive only. Yeah, I think option D is correct here. Okay. D. Next question you see. Sixteenth one. See, 16th one, option C is correct. No matter whatever the number of moles you have, okay? Because if you see the derivation of this, delta H is equals to delta U plus P delta V, we can write. Okay? Delta H is NCP delta T. Delta U is NCV delta T plus P delta V. Now in this, we are dividing by N delta T, both side. So whatever number of moles you take, N delta T, whatever number of moles you take, it will get cancelled. Okay, and we'll get Cp minus Cv is equals to R. This term is nothing but the gas constant. So this relation is true for all the value of N. Whether you take 1 mole, 2 mole, 10 mole, whatever it is, Cp minus Cv is equals to R is always correct, and hence option C is correct. Question number 17. We will not use Cp minus Cv is equals to NR. So I mean, it is always R. That's what the derivation we have here. You see this one. That's why I have done this. P del V by N T is nothing but R. Okay. So this is what it comes over here. So this already includes this number of moles term here. So you always write Cp minus Cv is equals to R, not NR. Clear? What is the answer? 17th one. 17th one, Amog and Shreyas is getting B. Okay, you see, molar heat capacity of water at constant pressure is 75 joule Kelvin per mole. So Cp is given 75 joule Kelvin per mole. Mass is given, that is, oh sorry, Q is given heat, 1 kilojoule means 1000 joule. Okay, and mass is given, that is 100 gram of water. 100 gram of water. The increase in temperature, see, first of all, these are the data given. We have to find out increase in temperature, right? Delta T or T. Means whatever this term we have to find out, the unit of this must be Kelvin. See, if you do not know anything, then what you can do, that's what I'm trying to make you understand. Right? Q delta T is equals to Kelvin. It means you required Kelvin over here. Right. For that, what we have to do, this is the term we have, which is Cp, joule, Kelvin, and mole, which we can write like this. You see, joule per Kelvin into mole. So what we'll do, we keep this K, we have to write this in the numerator to get K over here, right? Because delta T we have to find out. So we'll write what? 1 by all this term. 1 by joule per Kelvin into mole. And since joule we have to cancel out, so we'll multiply by joule, right? Mole is there in the numerator, so we have to cancel out. So we'll divide by mole. Now you see, what is this term? One by one, you just see this. This is, we know, 1 by Cp into this joule is what? Q into 1 by mole is what? The mass of the water, which is nothing but 1 by mole, you let it be now. So you see, this is what we have to have, and all these things are given in the question. 1 by Cp is nothing but 1 by 75, Q is 1000, and 1 by mole we have to find out, mass is given. So 100 into 18 molecular mass of water. Right, when you solve this, you'll get the answer 180 by 75. Right, so that will be 180 by 75. And that will be 2.4. You see this? 2.4. And since this term is nothing but Kelvin, so 2.4 Kelvin means this gives you the delta T 2.4 Kelvin. This is what you can do. If you do not know any formula, since we have to find out Kelvin, you should just try to manipulate these terms in such a way by multiplication and division, so that finally you'll get Kelvin and you'll get the answer. But if you write down the formula directly, the formula is Q is equals to NCP delta T. Q is given, number of moles we have, Cp we have, delta T will find out, that will be Q divided by N Cp, which is what we have done. Q divided by N Cp. This is what we have done there. Okay, so it's B. Option B is correct. Question number 18. Solve this question, then we'll take a break after this. See, in this question, question number 18, I'll tell you that this you must remember this formula, okay? The molar heat capacity for any process is given by C is equals to CV plus R divided by gamma minus 1. This is the formula we have for any process. Now you see a monoatomic ideal gas, this you have to memorize. Okay. A monoatomic ideal gas undergoes a process in which, just a second, I'm coming. Okay. So molar heat capacity can be given by this expression. Now you see the question is a monatomic ideal gas undergoes a process in which the ratio of P to V at any instant is constant and equals to 1. Okay, so next formula is, next thing is given, P by V is equals to 1. So constant, right? Which we can write it as P V to the power minus 1 is equals to constant. Now if you compare this with PV to the power gamma, gamma value is minus 1. It means in this process, whatever process the question is here, for that process the gamma value is minus 1. Okay, this is again like one of the method we have, in which they'll give you the P and V relation, okay, so that we can obtain the value of gamma, and then we can find out the molar heat capacity, right? Now what is the molar heat capacity of the gas? So this gamma will substitute over here. So C is equals to CV plus R by 2. CV plus R by 2, and CV we know it is 3 by 2 R plus R by 2. So it is 2 R or 4R by 2. So option A is correct. We are getting minus 2. Oh, sorry, I made a mistake here. Sorry. I made a mistake. It should be 1 minus gamma. My bad. It is 1 minus gamma actually, not gamma minus 1. No, it's not. See, actually, in this question, you first of all, you see, this is the formula we have. Have you done this? I think I have done this question once in the class, I guess. This formula. Molar heat capacity for any process is this. We have CV over here, not CP. Now here you see this question, a monatomic ideal gas undergoes a process in which, you see, there is a process, we have a process in which P by V is equals to constant. This is what the information we have, and that is it. Did you understand, Sanjana, Lalita? Okay, just you remember this formula. However, we hardly have uses of this formula. Okay, but if the question like this, if they haven't mentioned about the process, whether it is isothermal, adiabatic, and all, and they have given the relation of pressure and volume, so with that relation and this formula, you can easily find out the molar heat capacity. Okay, so this formula is very limited use we have when the process exactly is not mentioned in the question, and you must have some relation of P and V, or by any other way they have given your gamma value. Okay, then we can use this formula. Correct? And we have here CV, not CP. Must remember this formula. Question number 19. Can we take a break now? We'll start this question after break. Yes, or should we continue? Tell me. Okay, so we'll start this question after the break. Okay, we'll start sharp 7. Okay, 6:47 now. We'll start at 7. Okay, so we'll start at 7. Take a break. Okay, guys, can we start? Question number 19. Tell me the answer. Tell me the answer. Question number 19. All of you are getting A. Okay, so for adiabatic process, what we can write, T2 by T1 is equals to V1 by V2 to the power gamma minus 1. This is what we have used. Right? This is what you have used. Tell me fast. You have used this relation only. So for this relation, we can also write this P1 V1 to the power gamma is equals to P2 V2 to the power gamma. Can we use this also? Like this is also true. We can use it or not. That's another thing. But if this is true, this is also true. Right? And if this is true, according to the question, it has constant external pressure. P1 and P2 are constant, right? And that is equals to 1. So P1, P2 gets cancelled. So we'll get V1 is equals to V2. Right? And then we'll get T1 is equals to T2. Correct? But since there is a adiabatic change with change in volume also, so temperature cannot be same. And that is why we cannot use this expression here. Even this also we cannot use. See, we can use this expression when the pressure is not constant, the external pressure is not constant. You understand? Because we can write this relation for temperature volume, for pressure volume, for temperature pressure also. Correct? So now in this case, what happens? Since it is an adiabatic process, adiabatic change it is, right? So del Q is equals to 0. And hence we can write del E is equals to del W. Del E is nothing but NCV delta T, that is T2 minus T1, which is nothing but T, and del W is minus P V2 minus V1. Okay, N is given 1 mole. CV formula we have, CV is equals to R divided by gamma minus 1. Gamma for monoatomic gas we have already, that is 5 by 3. And R value will also have 0.0821. All these value will substitute here and will get the answer. And finally you will get T2 is equals to, or I substitute 1 by R divided by 5 by 3 minus 1 into T2 minus T is equals to, external pressure is 1 and this is 2 minus 1, that will be equals to minus 1. And when you solve this, this T2 becomes T minus 2 by 3 into 0.0821. This question I have already discussed in the class. Especially in Rajinagar, I have discussed this question. I remember this. And I told you, since external pressure is not variable here, it's constant. So we cannot use this expression here. Since with this expression, this is also true, and this is not the case we have. 19th D is the right one. Right? Answer is option D. 20. See, in this question is also a different question we have. I'll do this. You see, water is brought to boil under a pressure of 1 atmospheric when an electric current of 0.5 ampere from a 12 volt supply is passed for 300 seconds. Okay, so the enthalpy change here is nothing but the work done, which is equals to I current into volt into time, IVT. I is given 0.50 into 12 volt into 300 second. And this del H value is 1800 joule, which is nothing but 1.8 kilojoule del H. Okay. Now it is given that the resistance in thermal contact with it, it found this gram of water is vaporized. Okay. So 0.798 is equals to how many moles? Okay. So number of moles of water which has been vaporized is 0.798 by 18. Why we are calculating number of moles? Because we need to find out the molar internal energy. So we have to have molar enthalpy for that. Del Hm is for molar enthalpy. And then that will be equals to molar internal energy plus del Ng RT. This is what the formula we have to use, right? So we have to convert this enthalpy into molar enthalpy. Okay, and how do we do that? Del H, or we can write the molar enthalpy of vaporization. Enthalpy of vaporization is equals to del H by the number of moles of water that has been vaporized. So that will be equals to 1.8 divided by 0.798 by 18, and when you solve this you'll get 14.6 kilojoule per mole. Okay, and again when water vaporize, H2O liquid converts into H2O gas or vapor. So del Ng value for this reaction is equals to what? One only one gaseous molecule we have. Okay, now we'll substitute this term here. So del Em we have to find out. That will be del Hm minus RT, because del Ng is equals to 1. Del Hm is 40.6 minus RT will substitute since it is in joule. So we'll write here 8.314. It is joule. So 10 to the power minus 3 becomes kilojoule. And temperature is what? 373.15 Kelvin. So when you solve this, you'll get 37.5 kilojoule per mole. So answer is option A. Internal energy per mole is nothing but the molar internal energy, right? So when you have to find out molar internal energy here, this you must have to convert into molar enthalpy. And for that, the enthalpy per unit moles gives you molar enthalpy. Clear? This is actually, when you provide current into this, right? See how the water boils. You have a coil actually, right, through which you provide current, right? And when you must have seen that uh, water heater, that rod that you have, we put into water the bucket, and we connect this with the switchboard, and we provide current into it. Okay, so what happens in this process? It is nothing but the water gains the latent heat of vaporization, which is nothing but the enthalpy change, right? Water gains energy, this current passes through, right? Water gains energy, and then it starts vaporizing. That is nothing but the boiling of water, not vaporizing. We cannot say it's a boiling process actually, right? With the help of this rod heater that you have. Okay, so when this water gets vaporized, so its enthalpy will change. So what is that change in enthalpy? That is what we have calculated here. I into V into T. I current, V is the voltage, T is the time, right? So this is simply enthalpy change in the water. This is the molar enthalpy change, or molar enthalpy of vaporization. Clear? Next question. Do this one. See, this pressure is 1 atmospheric here, and here it is 0.5, 22.44, 44.88. This is 3, 1, and 2. See this diagram. Okay, all of you see this. I'll just remove it off then. 0.5, 1, pressure and volume axis we have. Correct? Now you see this question. Done. What happened? Should I solve this? Amog is getting A. Others? See, this question is very simple and straightforward. First of all, you see from 1 to 2 you are going, right? Constant pressure. Volume is getting doubled, right? So we know when pressure is constant, the volume and temperature is directly proportional. So if the volume V gets 2V, T also gets 2T, right? So at 1.1, if the temperature is T, then at point 2, the temperature will be 2T. Okay. Now 2 to 3, you see, volume is constant, pressure becomes half, right? So we also know when volume is constant, pressure is directly proportional to temperature. So when the pressure becomes half of P, the temperature also becomes half of T. right? So at second point, the pressure is 2T. So at third point, pressure becomes half, temperature will also becomes half, so it is T. Now you see the option. 27, if T is 273, then 2T will be 546, 273. Option A is correct. Understood. Fine. Got it. One more thing, what you can do at this point, you see pressure is 1 atmospheric, volume is 22.4 for 1 mole of gas. It means this point is at STP, right? So temperature will be what? 0 degrees Celsius. That is 273 Kelvin. This is what we have here. And then now we can easily do this by gas law. Right? Next question. '22. Same question, del E for the process. Yes. Hello. Tell me. Question number 22. What is the answer? Delta E we have to find out. Just use the formula NCV delta T. 1 to 2 temperature you have already, right? NCV delta T you have to use. Shreyas is getting D. Is it D? See, delta E is equals to NCV delta T. So number of moles is 1. CV is given 3 by 2. R is 8.314 into 10 to the power minus 3 kilojoule. And delta T is what? 273 Kelvin. Are you getting 10 to the power 3 or 10 to the power minus 3? 10 to the power 3 or 10 to the power minus 3? Tell me fast, we'll solve one more question. Your answer will be B, but I think it should be 10 to the power minus 3, right? .4, what is that? Only 3.4 you are getting. Why so? See, delta T is temperature at 2 minus temperature at 1. That will be 546 minus 273, 273 only. 1 into 3 by 2 into R. Because CV is equals to 3 by 2 R. You see the formula we have here? Yeah, it should be, yeah, it's then 3.4 joule. It's fine then. Yeah, this is correct actually. I didn't see this option. Oh no, it's minus. It should be plus. No, I think the option is wrong here. Either we should have 3.4 into 10 to the power minus 3 kilojoule, or it should be 10 to the power 3.4 joule, I think. Yeah, any one of these could be the answer. 3.4 joule or 3.4 10 to the minus 3 kilojoule. Okay. One more question we'll solve for today, the last one for today. The heat of sublimation of iodine is 24 calorie per degree at 50 degrees Celsius. If specific heat of solid iodine and its vapor are 0.055 and 0.31 calorie per gram, find the heat of sublimation of iodine at 100 degrees Celsius. Okay. You see, this one, you must have used this equation in physics, that is Kirchhoff equation. Usually it is not there in chemistry. They don't ask this question based on this in chemistry. The equation we call it as Kirchhoff's equation, and that is change in the change in specific heat delta of Cp is equals to delta H2 minus delta H1 divided by T2 minus T1. Delta H2 is the enthalpy change at temperature 2, T2. Delta H1 is the enthalpy change at temperature T1. Okay. So basically, change in enthalpy is equals to change in specific heat capacity into the temperature difference. Right. Now, in this question, you see, we have to find out the heat of sublimation of iodine at 100 degrees Celsius. Right. T2 is T2, here it is 100. Right. T1 is given 50. Delta H2 we have to find out. Delta H1 is given in the question, and that is 24 calorie per gram. Right? Cp is given. Delta Cp is equals to what? I'll write 0.055 minus 0.031 calorie per gram. So when you use this, all these terms, so delta H2 minus delta H1 will be 24 is equals to 0.055 minus 0.031 into 100 minus 50. When you solve this, you'll get delta H2 directly, and that will be around 23, which is 22.8 calorie per gram. Okay. You see, one thing that they did not ask any question based on this formula. Okay, in chemistry, right? But you never know what they are going to ask. So this is again one formula we have. You must have used this formula in physics, right? So this formula again you have to keep in mind. Okay, with the data given in the question, you will understand like what formula we have to apply. Is it clear? Option B with the same result. I think you should get option A. Check your calculation, Shreyash. Understood, all of you? Okay. So we'll wind up the class here only. Okay, next class we'll solve 10, 12 more problems on this, and then we'll move on to the next chapter. Correct? All of you must read out inorganic. Okay, these 2 months that you have, 1 month, you must read out inorganic from NCRT. All the chapters of inorganic, environmental chemistry, polymers, and all these things you must study every day, one chapter every day, at least 4, 5, 6 pages. Okay, don't leave that. All factual questions, you must have observed that you will be having some difficulty in you will be getting some difficulty in the exam. Are we getting option B? Okay, I'll cross check this. I think the formula is correct. This is the formula. I think I read H2 minus H1 by T2 minus T1. Both will write like this only. Okay, I'll see this calculation. I'll cross check this. Okay, let it be now. Right. So inorganic, you must revise. Okay. Don't leave that every day. Whatever you are studying, you study. But you know, you must read out 4, 5, 6 pages of NCRT inorganic every day. It will take half an hour hardly. So must do that. Okay. Anyway, so we'll see you in the next class. Okay, we'll start from here only. We'll solve some more 10, 12 problems in this chapter, and then we'll move on to the another chapter. Okay, thank you all.